Yeah, so hello and welcome student for today's lecture. So this is our course MA425 Topology. Okay, and this is lecture number 15. Lecture number 15. Okay, so recall in our last class we have discussed about quotient space. Okay, space. Okay, so we have some set X. And what do, you just try to partition it. The partition can be singleton also containing. Okay, and this is extra is collection of all partitions. Okay, you can say that this is collection of this x1 x2 whatever you can find, infinite, doesn't matter. Okay, and then you are sending so what does that mean? That means every point on this going to the single point here. Okay, so all the points belong to the same portion is now we can identify all the point by a single point. And then obviously there is natural projection. You can say this projection map that sends all these points to single points, right? And this becomes the quotient map, and this is the quotient space. This extra is the quotient space of X. Okay, so and the question is that so today I will discuss many properties. One such property is what about if you restrict the quotient map on kind of a proper subspace of that thing, is this still a quotient map or not? And then we will prove that this may or may not be. So in general this may not be. If we have some certain condition, then it will be. Okay, so let me just discuss this one by one. So let we have say P from X to X star. Okay, be a quotient map and you choose a subspace which is saturated with respect to P, and A is a subspace of X, not a subspace of X. So A is subspace of X such that A is saturated with respect to P. So what does that mean? That means whenever you choose this is kind of full inverse image of something here. Okay, so maybe let me not write down the symbol, so you may be feeling problems. So let me start with general space. Okay, general space Y. Okay, you can do it by X star, obviously, no problem, but then it will be kind of A will be union of this some of the partitions. Okay, so but anyway, so let me start with general definition. Okay, and this saturated with respect to P, and then obviously you can restrict this P on A, so you can have this Q from A to the image of A with respect to P. So this is the subspace of Y, right? So this is nothing. This Q is nothing but P restricted to A, right? Restriction map. So the natural question is that whether the restriction map is a quotient map or not. we have seen inside continuity that if you could restrict a continuous map, it becomes a continuous map, right? So what about this kind of property, quotient maps? And the answer is it is not always true, obviously. It is true for some cases. So case number one, let me first prove this. If A is either open set or a closed set, then Q became a quotient map. This is one case. So if A is either open set or closed set, then the restriction map Q is a quotient map. Okay, so now but if it is neither open nor closed, then I don't know. So it may or may not be again. Okay. So then also theorem is not true. There are examples for both cases. But in the case when it's either open set or closed set, then this Q must be the restriction must be a quotient map. Okay. Okay. So what does that mean? That means if you restrict a quotient map on a saturated open set or a saturated closed set, then restriction will become a quotient map. Okay. Now how do you prove this kind of statement? Okay, so let me give a proof, but before that let us just discuss one observation. Okay, so this remark, let me prove some remark. Okay. So remark 1, remark A, whatever. So you see that whenever if you take a subset B of this image of A under P, okay. So let me just draw a picture. Here you have X, here you have a Y, and what you have done. So you have sent a map P, and P say map it to something. P is quotient map, so it's on to, okay, everything. Okay, and you have something saturated open set or closed, doesn't matter, A, and then with respect to that the image may be something like that, whatever. This is P of A. Okay, now if you restrict the map here, then this is also quotient map. This is first thing you just want to know. Okay, and to prove this, I need some general remark. So if you start with open set inside PA, so for example, inside PA you choose some open set and take the pre-image here with respect to P. So you can take pre-image with respect to the Q or with respect to P also, right? And the answer is that they both are same actually. Okay, then this P inverse of that B is same as Q inverse of V, and that is because that P is actually A is actually a saturated set. That's why the pre-image is contained inside this full. Okay, so how to prove it? So prove this is the proof is simple. So just give me one line proof. So the P inverse V is okay. So B is a subset inside P and A is saturated. So P inverse B, P inverse V intersect with A non-empty, right? Because they intersect. That's why B is inside PA, right? That's why. So you have elements which are intersect in both the set, and because as A is saturated and A is saturated. What does that mean? That means P inverse B actually sitting inside A. It contains everything. Okay. And thus so now because this is a subset of A, so we can talk about the pre-image of B with respect to the map Q, right? So that means, so this means this is actually equal to, because on A, P look like Q, right? So P inverse B on A is nothing but the Q inverse of V, right? They are same, right? This is a simple observation. Okay, a simple remark. And number B, remark or observation B. Okay, so this is so if you start with a set U inside X, then you see that because of P is a quotient map, you can have P U intersection A is nothing but P U intersection P A. So what does that mean? That means, so you choose something U here, okay, and you find out the image under the map A, so it will be something like something say this, okay. And if you take U intersection A, which is say this portion, intersection portion, okay, and the image will be exactly the intersection portion here, which will be full images and then take the intersections. And that is true for only quotient map, okay. Okay, so obviously one part is obvious, so that is so proof. So one part is obvious. So which is obvious. You always know that the P of U intersection A is always subset of PU intersection PA, right? Because if you choose anything which is inside U and A, then image will be all inside P of U also and P of A also, so it is inside the intersection. So this part is obvious, right? Now converse part we need to prove. So conversely let you choose something, say Y belongs to PU intersection PA, and then I have to prove that this Y is coming from image of a point which is inside U intersection A. Then I am done. So what does that mean? That means, so this implies Y equal to P of U for some U belongs to U, for some U belongs to U, and also Y equal to P of some small a for some A belongs to A, right? Clear? Now obviously this point P of A is a point inside P of A, right? And hence P inverse of P of A, this is inside. So this is the fiber of PA with respect to PA, because A is saturated, so this is inside A, as A is saturated. Okay, but P inverse of PA is what? So so now see PA equal to PU also, so P inverse of PA also contains U, right? So this implies that both U, obviously A is inside A, but U is also inside A, right? Because PA and PU are same, so P inverse of PA is also contains U, and P inverse of PA also contains A, because A is saturated, so both A and U belongs to A, right? So that's what that means. That this means U is element of U intersection A, and what is U? So U, what is P of U? P of U equal to Y, right? Clear? So P of U equal to Y. So what does that mean? That means thus this implies Y is element of P of U intersection A, and hence PU intersection PA is a subset of P of U intersection A, and hence they are same. And thus for saturated saturated subset it is same. Okay, clear? Now we will go to the proof of our first statement. So proof of, now what was the first statement? The first statement, where is that? Yeah, So first statement we are saying that if A is either a open map, so A is saturated is given. So I'm asking, what I'm claiming that restriction map of a quotient map on a saturated open set or saturated closed set is also quotient map. Okay, this is the theorem we are going to prove. So proof of one. Okay, so what is given? It is given that P is a quotient map and A is a saturated open set or closed set. So let us assume. So let me do it for open set, closed set. The proof is same, similar. You don't have to do anything extra. Okay, instead of open set, you just prove the pullback. So okay, so I will tell you why you need to change. Okay, so let A be a saturated open set of X. Okay, and obviously the original what I need to prove? I need to prove that that obviously one thing, that P is given what? P is given quotient map. So P is so on part, let me first tell that as P is a quotient map P is continuous. Okay, and thus Q is also continuous because Q is a restriction map. Okay, so what does that mean? That means you already know that that the restriction map Q is continuous is there. So what does that mean? That means it pulls open set back to open set, right? So thus what? So if suppose you have open set, say you choose open set, say if B is open in P of A, then Q inverse V is open in A. That is no, because Q is continuous, right? Now conversely, what I need to prove? So conversely, assume that. So we need to prove that B is a set such that Q inverse B is open, and then I need to prove that V is open in P of A, right? So conversely, let V subset of PA such that what happened? Q inverse V is open in A. So I need to prove that V is open in A. But Q inverse V is what? But Q inverse V is same as P inverse of V, right? Inside A. This is, we just prove it, right? And we know that P is a quotient map. So if you have a P is a quotient map, means as P is a quotient map. Okay, so P is a quotient map. Okay, no, before that I need to just check one more thing. P is quotient map, but P inverse V is open in A. This is important thing. But A is also open, right? So this implies P inverse V is open in X. Open in X as A is open in X, right? Open subset of a subspace is also open inside the full subspace. So P inverse is open in X. And now I am done. as P is a quotient map. And P inverse V is open in X. We go so we know that the image of under P is also open, so we have V is open in that P over here, right? Done. So this is the thing we know we need. Okay, yeah, I mean actually I should say B is open inside Y, but then B is inside PA, so it's open inside PA, right? So thus that Q is a quotient map. This gives the proof. Okay. Now instead of if you don't have open, instead of open, if you want to use the close property, then you start with, suppose this close map. You start with what? You start with that A is a saturated closed set, and Q inverse B is a closed set inside A, and then Q inverse B equal to P inverse B. So P inverse B will be closed inside A, and A is closed inside X, so P inverse B is closed inside X. And then obviously, because this is quotient map, so it also map P inverse the closed set to closed set, right? So you also map P inverse V to the closed set to the set P, which is a V itself, right? So if a map is sense so then it is what you are proving, that subset is closed if only B is closed, if only P inverse B is closed, right? So this is the same definition as quotient maps. So the proof is same. So instead of open set, if you have is saturated closed set, the proof will be similar proof, just you need to change few places. Okay, else everything is same. Now I will try to prove that other part of the number 2 of this theorem, and in this part it tells you that so suppose you don't know about the set A, how it look like. If you know about the map, then also you can say, okay, so if P is either open map or closed map, then also you can say then Q is a quotient map. Okay, so in case if you don't know about the say how it look like, you can talk about the original quotient map. What kind of quotient map is that? Open quotient map or closed quotient map? If it is any of those things, then it is true. But remember, all the quotient map may not be open and closed. It may be open, may be closed, may not be open, may not be closed. Okay, so you don't know. Okay, and if this homomorphism, then it is both open and closed. Okay, so the proof, how do you prove it? So suppose I am assuming that let P be an open map. So this is a quotient map which is also open map. Okay, and then I need to prove what? I need to prove that okay, so one part is always obvious, that Q is continuous because P is continuous, right? Now the next part we need to prove only, right? So let again you choose the B subset of PA such that P inverse of Q inverse of B is open in A. Okay, this is given, and also we know that Q inverse of B equal to P inverse of B. So this is open. in A, right? So this is open inside A, and because this is a subspace, so open set are what they are actually coming from intersection of open set and the original space. So thus you can write down this P inverse of V is nothing but some U intersection A, where U is an open set of X. Okay, P inverse V is Q inverse V, which is open inside A. These open sets are nothing but the intersection with some open set of the original space, right? So and also you know that P is surjective because quotient map is surjective. So as P is surjective, what do we have? So we have P of P inverse of V. This is V. P of P inverse of V is nothing but V. If it is not surjective, it can be a proper subset of V, but because this is surjective map, so this is V, and hence what you can write down? You can write down thus you can write down your V is nothing but P of P inverse of V, and you know that P inverse of V is nothing but U intersection A, but because A is saturated, and hence it is PU intersection P of A. Okay, PU intersection P of A, and now you also so I need to prove that V is open set inside P of A. So it is enough to show that PU is open inside Y, but that is obvious because see P is quotient map, and I already proved that what is that P is open map. So as P is a open map, we have PU is open in Y, okay, and thus V equal to PU intersection PA is open in PA. So it's done. So we just prove that every image of every if P inverse of V is open, then V has to be open inside PA. Okay, and that proves that this is open set. Okay, so this is one very important property that we have learned for restriction maps or quotient map is quotient or not. If you need these properties, this is a sufficient condition for that thing. Now one can ask some other question. What about question? You can the simple question. How about composition? So how about compositions of quotient maps? They are quotient map or not? Okay, for example, you have X, Y and Z. Okay, and you have something say P1 and P2, then can you say that composition of these two are quotient maps? And that is simple. You can easily check that so if you are going to P1 compose P2, or rather sorry, P2 compose P1, so you are sending open. First of all, these are all continuous maps, so composition of continuous. So P2 compose P1 is continuous. One part is obvious. Now to prove the other part, what did you prove? You prove that if the pre-images with respect to these, okay, so what is so this is P1 and then P2, so this is the composition maps from X to Y, and what is the inverse of that map? You take this inverse, and now which is that this inverse is nothing but there is some issue here. What is the inverse? The inverse is nothing but P1 inverse of P2 inverse of U, right? So first you take the inverse here, and then with respect to P2 y inside that with respect to P1 right. And now this is obviously because so you need to check that if this is P2 P1 inverse is open, then U is open or not, and this is open means this is open, P1 inverse or P2 inverse of U is open, right? But P say P1 is a quotient map, so that will gives you the P2 inverse of Q is open in Y. Again P2 is a quotient map, so that will gives you that U is open inside X. So this is obvious. So the answer is yes. Answer is yes here. It's always composition of quotient maps or quotient map, right? But the question is that on a quotient pair, can you define a quotient continuous maps always? Is this true to define a continuous map always? So to construct these continuous maps on quotient space, we need this following theorem. So let us prove this theorem. So suppose we have a quotient map. So P x to y be a quotient map, and you have another space. So let Z be a space means topological space. Always I am talking about space such that, so you have a map from such that you have map G from X to Z, which is constant on this pre-image of singleton set with respect to Y, constant on pre-image of singleton set. Okay, so whatever singleton set you choose, it is this for all Y belongs to Y. Okay, so you are defining. So the quotient map means what? So it may not be one, right? So for every point Y there might be many pre-images inside X, and you are defining G constant on all those points. Okay, so if you do this thing, then G will induce a nice map. Then G induces a map, say F, which is from X to Y, that quotient space, Y to Z, Y is my quotient space, okay, because P is the quotient map, okay, such that the diagram commutes. So what does that mean? Such that, so let me such that this F compose P is nothing but G. So this is called commutative diagram. Let me draw a picture. So you have X, and then you have this quotient map P from X to Y, and suppose you have another map X to G, which is G, and if G is such a map that which is constant on three images of every point of under the map P, then you can have a map from here to here, and this is my F. Okay, and this is called a commutative diagram. So what does that mean? That means this F compose P is G. So if you start with the X, if you go with the element P and then go with F to Z, and you will reach the same point if you go from X to Z with Z. Okay, with the map G. Okay, so this is obvious, this portion, because this is obvious because you choose a. So how to define the map F of Y? So Y is an element here inside Y, and you go to P inverse of Y, and so P inverse of Y here inside X, and you know that every point of P inverse 1 and map to the same point. So you write down that G of P inverse of Y, right? So what does that mean? That means this is G compose P, and hence F compose P is nothing but G. Okay, because F is nothing but G compose P inverse kind of thing. Okay, but this is the map. Okay, so this portion is obvious. But what is interesting part is that this map F is depend on the map G with very nice property. So property number 1 and 2. So 1, that F is continuous if and only if F is continuous if and only if G is continuous. Okay, this is number 1. And F is a homeomorphism. Sorry, F is a quotient map if and only if G is a quotient map. Homeomorphism I will come later. First, let us prove the quotient map. So maybe let me give the proof of this first. Okay, proof. Then I will prove the other part. And you already know that F compose P equal to G, right? So if F is continuous, so is G, because P is also continuous, right? P is a quotient map, so it's continuous. So then so is G, composition of two continuous map is continuous. This part is obvious. Part 2, conversely, not part 2, conversely, let G is continuous, and I need to show that F is also continuous, right? So what does that mean? That means so what I need to prove? I need to prove that F is continuous from Y to Z. So in inverse of full block of open set is open. So let V subset of Z is an open set, and I need to show that F inverse V is open, right? But what is if V is open set and G is given continuous, then what does that mean? Then G inverse of V is open in X, right? Because G is mapped from X to Z, so G inverse of V is open in X. But what is G inverse? So G inverse, you look at this map. G inverse F compose P equal to G. So G inverse means P inverse compose F inverse, right? But G inverse of V is nothing but P inverse of F inverse of V, right? Is that okay? Now what is given? It is given that the map P is a quotient map. That is given from the beginning. Okay, and if P inverse of a element is open and P is a quotient map, this implies that set is still open. So this implies F inverse of V is open as P is a quotient map. Okay, and thus we are done. So that I need to prove, right? F inverse V is open. So thus F inverse V is open in Y, and so F is continuous. This is the proof, right? So F is continuous. Now the part 2 of this theorem, that F is quotient map if and only G is quotient map. So F is quotient map if and only G is quotient map. Okay, now how to prove this? So again, one part is obvious. If F is quotient map, G is quotient map, right? So proof, because the composition of two quotient map. If F is quotient map, so is G. That is obvious because composition of two quotient map. Now conversely, conversely Firstly, let G is a quotient map. Okay, so I need to prove the if is quotient map. So what does that mean? That means I need to prove that given any set, say V, such that if inverse V is open inside Y, then V is open inside Z. This is I need to prove. So let V subset of G such that if inverse V is open in Y, so we need to prove that V is open inside Z, right? But if inverse V is open, and if inverse V is open, then we know that P, what is the, okay, so let me write down. Now you see G inverse of V is nothing but P inverse V, P inverse of F inverse of V, right? Because F compose P equal to G. Now I just got that this is given that F inverse B is open. If inverse B is open and P is also, you know that P is also yeah, so you also know that G inverse of V is what is that quotient map. Okay, so what does you know? So now what is the property? So this is continuous functions and this open set. So G inverse B is open. So this implies that G inverse V is open in X as P is continuous. Is open quotient map is a continuous map, right? So pullback of open sets if inverse V is open inside X, which is P inverse F inverse B, but that is equal to G inverse B. So this is open, this is continuous. Okay, so G inverse B is open inside X. Now G inverse B open inside X, but G is quotient map. So V is open in Z, right? Now as G is a quotient map, and G inverse V is open, this implies V is open in Z. Done. So this is the thing we need to prove. What we need to prove? We need to start with a subset V such that if inverse V is open, and then need to prove that V is open. We just prove that V is open in Z. Okay. So that proves. So this proves that F is also quotient maps. Okay. Now what is the important thing here? So with the help of this thing, first of all, we construct the continuous functions. That continuous function on quotient space will be what? That will come from continuous functions from X to Z, right? And as a corollary, we can have also, we can get the homomorphism property also. How? So let me write down corollary. So you have this G map from X to Z, okay, which is surjective, so on to, and you just define that star, the quotient space by what? So quotient space are actually elements are what? These are fibers of element of Z with respect to the map G. So this is G of kind of singletons, let's say. Okay, Z belongs to Z. Obviously, so what you are doing? So this is X and this is Z, and this is X. Suppose there are 2, 3, 4 points which are mapping to same points here. Okay, and then these same points. So what are the points mapping to same points? You are making those points a single point inside X in X star. Okay, so then you become X stars. So here what are your elements? So the equivalent class are what? All those points which have the same image. So they become a single point here. Again this becomes single point here. If it is single point, then obviously equivalent class is single point. Okay, so with the help of this, so we can give a quotient topology on X stars. Okay, so pull back. So what is the quotient topology? So open sets are coming from these maps, open sets of X, right? Okay, so with the help of this we can have this theorem. So theorem 1 that tells you that G actually, so you have X to X stars, which is that obviously the quotient map, and X to Z is a G map. Then you can have the map here, which is F. Okay, so this is induced by G, and this map is actually a bijective map. See, originally the map G may not be bijective, but as you have identified all the points, single points which is mapping the same points, the new map F from X star to G is bijective. This is obvious. Okay, because the problematic points where many points is mapping to one, you just make it the single point here, right? So this map become bijective maps now. Okay, originally the map was only onto, that's because of this process you make it 1 1, so this is bijective. But not only that, so this is also homeomorphism if and only G is a quotient map. Okay, so if we, so F is a homeomorphism if and only G is a quotient map. So if you start with the quotient map, then you can reach a homeomorphism induced from the quotient map. Okay, this is first proof. So let us prove this thing. So obviously how to define, so we define that F compose P equal to G, right? This is the actual definition. And so if you know that F is homeomorphism, then G is quotient map, because okay, so what you need to prove? You need to say if P is continuous, F is continuous, so G is continuous. One part is obvious. Now second part is, okay, maybe I can assume continuity here also. This is good. Yeah, so this on to continuous maps, so I don't need to. Okay. Now homeomorphism are what? So if F is homeomorphism, it's also quotient map. So if F is a homeomorphism, then F is a quotient map. Okay, and P is already quotient map. P is also a quotient map. Thus G is so, right? G is also quotient map, because composition of the quotient map is quotient map. Now conversely, if G is a quotient map, then you need to show that F is a homeomorphism. But that is obvious because we just proved that conversely, if G is a quotient map, then if is a quotient map, right? That is the previous theorem we proved it. And F is a bijective quotient map. So bijective quotient maps are what? So this is open map, continuous map, and also this is bijective. So thus F is homeomorphism, right? Thus F is homeomorphism. So what does that mean? That means you can always construct homeomorphism on quotient space given from a quotient map. Okay, and another important property is that this quotient space may be Hausdorff T2. That depends on what is the space Z. So let me prove that. If Z is T2, then so is X star, the quotient space. So I can tell about quotient space T2 or not. That depends on Z, which is actually image of a continuous surjective map from X. Okay. And how to prove it? So this proof is also not difficult. So you choose 2 points. So let say x1, not 2 distinct points, right? Not equal to x2 in x stars. Okay, and then obviously if it's a homeomorphism, okay, so if it's a bijective map, obviously that is always true. So f of x1 not equal to f of x2 is bijective, so it's obviously injective. Now f of x1 f of x2 are element of z, right? But z is t2, so there exist open sets u and v in z such that what happened? Now f of x1 is element of u, f of x2 is element of v, and u intersection v is empty, right? And hence because this is bijective map, and then what happened? Then f inverse of u inside x stars and f inverse of v, they are also empty, right? Because if they are not empty, then u intersection v is not empty, right? So they are empty, and you see that x1 is an element of f inverse of u, and x2 is an element of f inverse of v, right? So f is a bijective continuous bijective homeomorphism. So f inverse u and f inverse v are open set, and now you will have 2 open sets such that they contains these 2 points and they have disjoint. Hence you can separate any 2 distinct points of x star by disjoint open neighborhoods, right? And hence x star is t2. This is the proof. Okay, so so is that okay? So this is disjoint neighborhood. So you are done. Okay. So what we learn? We learn that how to define or how to generate continuous maps on a quotient space with the help of another map, the arbitrary space, and also how to generate the homeomorphism from a quotient space to another space. So to check some question how if you know a space, if you want to know what is the quotient space look like, then you define that from space to another space a nice map, so that will induce a homeomorphism from the quotient space to that space. Okay, clear? Or rather, if you say the quotient space homeomorphic to a space z, so then the space z should have a continuous onto correspondence from the original space. Okay, this is the important things, right? Is that okay? So maybe let me just tell you. So you have x and you have x star. You want to know how the x star look like. It is enough to find out a space z and a onto continuous map. Okay, this is onto continuous map, and then you are done, because the moment you have onto continuous quotient map, or rather, yeah, even quotient map, let me assume that quotient map, if you have a quotient map, then you know that from this to this, this is homeomorphism, right? So this will become homeomorphism, and the moment this becomes a homeomorphism, x star to this is homeomorphism, and then you know how it look like. So this has a nice property. Okay, and not only that. Okay, so the quotient map you need to write down such a way that the elements of these are actually coming from these pre-images of the fibers of element of this. Then only, obviously. So this x has to be these. This has to be these fibers of single points z. Okay, then only you can do it. Okay, but this process is a standard process to to make that extra is homomorphic to this or not. Okay, there are many other process in you may learn in later. Okay, so I will stop here in my today's class.